Where is that thing actually?
Tiens, est-ce qu'il faut des masques?
Non, à chaque fois que tu besoin des masques.
Tu veux une pochette de masques au cas où?
Non, non, non.
Sûr?
Ouais.
Regarde, c'est là-bas, il y en a un.
Non, 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 ça va.
Tu veux autre chose?
Ah non.
S'il faut des stylos ou quoi que ce soit, tu me dis, je suis en haut, là, t'as mon numéro, il fait something.
Yes.
Ok?
Yes.
À la toute.
Here it is something weird actually. But I cannot find anywhere at home. Not scheduled, drawing is in progress. Yeah. I don't know why I'm not calling it.
Because you don't have the Zoom call here. I told you it was this one.
We now have to leave this.
You are in the meeting.
You have to share the call with me as well.
So I need to send you the invitation, right?
Yes. Where are you going to send it?
On Gmail? Or where do you want?
Yes.
Ah oui, le sous-marin, je pense, c'est là. Bonjour.
Bonjour.
Ah, je voyais plus gros. On l'a cassé. Avant Noël, on l'a cassé.
Ok.
C'est beau. Il est beau.
Ah. Ouais, ok.
Oui, donc c'est un live qui va Lina,
Ouais.
les papiers, c'est pareil, tu l'as gardé ou c'est toi?
Non, non, c'est moi qui garde.
Il faut donner.
Ok, je peux l'amener.
C'est les deux enveloppes.
Ouais.
Oui.
Ok. Et les autres feuilles aussi.
Les autres, c'est le temps. Ça, c'est les ouvrages avec les Ah oui, c'est les fauteurs. Voilà, par rapport au bureau, vous dites que tu l'as rendu non autonome. Non, ah, j'avais pas vu le latéral. Il est au-dessus, je ne te voyais pas, je voyais que ces deux-là. Oui, d'accord. Au début, comme on n'a pas encore cette plateforme-là, on a testé le mot sous-actionné. Ouais. D'accord. Ça, j'avais vu la caméra, je ne sais plus quand est-ce que tu m'avais montré dans où j'ai vu dans la réunion avec c'est bien une configuration de caméra. Il est très compact, hein, ce
I don't know why it doesn't show here the column there.
Vous avez compris ça. Ok. Oui. En fait, après le reste c'est du PDF parce que c'est du télépéage. Donc je vais lui mettre les. Je crois que j'ai rien de spécial. J'ai que la facture de repas hier soir.
It's from.
Oui, on peut donner. Bonjour. Bonjour. Guillaume, vous avez aujourd'hui je ne sais pas, oui, peut-être. Bonjour. Oui, ok.
Is it showing this screen?
Ouais, c'est juste celui-là. Et après, les autres, je vais lui envoyer par
Avec
PDF.
l'HTML.
Ils m'ont donné un PDF.
Attends.
Et le péage, il faut que j'attende 5 jours.
Yes, it's
Je
connected.
vais lui envoyer le péage. Ouais. Et donc, ça c'est juste le retranscription. C'est le seul truc où il y a un conflit. Sinon,
That's what they're actually want.
je vais mon nom dessus.
We don't want to share this, we want to share the laptop.
The right cable? Right over there?
Yeah, that's the only one I think.
Okay. Does that make sense?
I see. Wait. Again, it's showing this screen instead of the laptop.
Show which screen?
It should be showing this screen instead of that one in the projector.
Where's the controller?
Which one?
The gray one.
Salut Andrew, je t'avais pas vu depuis moi.
Salut, ça va? Ça va?
But it's not the TV.
So it's not linked to. You wanted the camera on this one.
No, we want this screen. No, here we want the video conference, the Zoom call. The Zoom call. Which it was in the Zoom call already. What we want is the projector to show the laptop, not this screen.
Maybe there's some camera.
Can we disconnect this screen from the projector? No. No, camera. No, activate the camera. Ah, mierda. But even when you activate the camera, it should be showing here. Yeah. Ah, no, you don't have. No, you don't have any camera.
Ça va? Bon, très bien.
Still showing this camera.
Change again. Change again to the conference.
Ah, no, that.
Okay.
That is okay now. If you share the screen,
Now, yes, now you can see it both. Yeah. Hey, you're a haircut man. Ah, yes. So it's working? Yeah, seems that it's working, yes. Okay. Yeah. Ah, it's just of the 1 meter distance. I think so. Yes. Ah, c'est bon là, non? Ah, it's voilà. C'est bueno.
Là, j'ai galère un peu avec le j'ai envoyé ma XP et fin août. J'attends depuis 6 mois.
StateEstimation. Nice.
Et je deviendra, c'est mon achat. Et
Donc après, là, il y a la personne qui a écrit le troisième rapport qui est en vidéo. Ouais, mais tu fais exprès aussi, en fait.
Il y a qui ça va venir en fait.
20 degrés.
Ça, c'est déjà ah oui. Non, bah, j'ai essayé de faire un peu ça.
this one should be unmuted.
Moi, j'aimerais. À chaque fois, ouais, je vais revoir ça. Oui, et alors, tu l'as dit, c'est une péché avec
What did you do?
ah, mais c'est quand même des oreilles, il vient de juger de
Activated.
No, but.
No, it's not.
Not activated? It's with the. No, it's with the.
I think it's okay now.
It should be fine.
I think.
I don't know. Maybe for calibrating the review when
Very cool, very cool. We got the demo, you know. I see. No, but this is a demo, you have to show. To show up. Avec la série sur le bâton. Hein. Ouais, c'est ça. C'est cool. Bon, vous avez passé des vacances, ouais? Oh, yes. Oh, oui, il y a tout le Mexique. Alors, bien mangé? Oui, c'est ça.
Ah,
Ready? Yeah, since my job these days, since the beginning of January. Okay.
Carlos will directly run.
Oh, but here it's okay. Look at the streaming.
The objective for this year. Exactly, exactly.
So the streaming has started already, right?
Will you hear?
Okay.
Yes.
Man, I hope I will understand something. Yes, man, it's very good. No, it'll be nice. This is yours?
Because we have 3 here and I don't know how
Non, this is easy.
No, we are only 6.
Ah, non, parce que je pense, non, non, moi j'avais des soucis, enfin, jusqu'à maintenant j'en ai encore. Et en même temps, je suis non, mais parce que il y a les autres qui il y en a 3 je peux utiliser par exemple, regardez, oui, je vois. Mais en même temps, il faut pouvoir faire l'électrode aussi, parce que la calibration est la même. On dit que c'est la même, on dit que c'est la même avec oui, t'as envoyé 14. J'ai vu le mail, mais. Mais ça serait bien que tu donnes la date qui
Je te donne l'exemple, comme ça tu peux faire le direct.
Parce que là, ça commence à fonctionner. Ça passe pas. J'ai le fait que j'ai repris. Oui, ça me remet un peu à la
Okay. Okay. For the picture we will see at least. Awesome. First time. I would like to thank Eva. Oui, mais après, je suis avec plus
C'est moi qui fais quoi?
Alors, il y a deux choses.
And small water for you there. Maybe sometimes you need to refresh. No, put down.
No, where it
No, put there.
But put it straight.
No, but I don't think it's like
Yeah, I like the last detail.
The remote?
Don't lay down, don't lay down.
I don't know if it's Carlos, right?
Tu peux voir
What is that? It's
I just came back. That's my excuse.
He was in Mexico, then he went to Paris and he came back yesterday.
Thank you. On a special occasion. Oh yeah. Which one? For this one? But it looks okay, Nina, in the video.
In the video it's okay.
Yes.
I just showed you there.
No, it looks good. Vale, vale.
J'ai vu un peu le. J'ai fait
¿Qué tal, Lucy? ¿Cómo estás? Hola, hola. Oh, increíble.
Final.
Sí, sí, sí. No, ahora me traje mi recuerdito. Recordote. Dale. Desde el día 1 hasta el día que me regresé. Oh, sí, sí, sí. Sí, fue exactamente, ¿no? Desde que llegué fue de... estaba comiendo sin tener hambre, ¿sabes? No tengo hambre, pero viene. ¿Y tú qué tal? ¿Cómo se lo pasaron?
Carlos is already connected or not? No? Did you send it?
Sí, sí, sí. Nosotros, ¿sabes? Sí, pero hay que ver el destino. Ay, sí, sí, me dijo. Mandó un mensaje para ver si yo puedo ir por allá. Y le dije, no, llegué la semana pasada. Sí, de hecho, llegué hace 15 días, pero me mandaron a una misión a París y llegué el jueves. Así que, bueno, ya. Todo el mundo,
No, it's nice when I did it. Yeah, just Tarek is calling him.
No, he's going to go. Should we keep?
He's connected?
Yeah, he's fine.
Huh?
Maybe in few seconds we'll be connected.
Sorry?
In few seconds we'll be
Okay,
connected.
okay.
Okay. He don't have any problem. He said he's just going to do it.
On est 25, donc c'est bon. Il ne faut pas faire entrer autre, c'est ça.
Vous pouvez assister là-haut.
Ouvre la fenêtre là-bas.
Maybe better the ones in the back.
Open, please.
Je suis responsable, mais s'il y a quelque chose. On a Covid, il faut dire.
Je commence à me pousser déjà.
Ouais, ça y est.
Yeah, I thought it was on my couch, so it takes maybe 10 minutes.
J'entends ça. Ziad, prends le micro à côté de toi.
On a testé, il porte bien celui-là.
Non.
Is it a problem?
No, no, it's okay.
Because I will come in here and talk, or I think it works even in.
Yes, hello? Hello?
No.
I know it. Yeah, just put it on. And
May not. You think he's trying to use the link from yesterday?
No, I sent him an email in the morning today.
Okay.
No, yesterday was just,
Okay.
C'est pas le même système YouTube, puis sur Next.
oui, c'est YouTube qui
yeah, YouTube et Zoom, les deux. It seems like the link that we sent him is not working.
I sent him a new link in the morning.
Okay.
Yes? And it's not working?
Yeah, he's saying that the meeting not started yet. The meeting is not started yet. This means that you did some. Maybe you planned the meeting for tomorrow or something.
Everyone else is.
Yeah.
Non,
No, it works.
c'est tourne depuis ce matin.
Ça marche.
Yeah. Okay. Yeah. Okay. Yeah. Welcome.
Want to stop?
You have to open Zoom, right? Open your link first.
But I'm in Zoom actually.
C'est ça, il y a les
Yeah.
il y a deux connectés.
It's two people connected. So can you check?
Yeah, I'm sending him again the same link. It's Cease Invest. Yeah.
Send him an email within the same invitation
Yeah,
you
that's
sent
what
me.
okay.
The same invitation you sent to that laptop.
Or I just send him this one because I should be. Okay.
Ah bon? Je savais pas, hein.
I sent him the link again.
A new one or the same?
Of this Zoom meeting.
C'est pas l'outil Zoom CNRS.
Yeah.
Maintenance.
Yes.
There?
Yeah.
You should have only two people.
No, there's Carlos. I can see here.
You can see. Okay.
Yeah.
So I'll try to talk to him first.
Carlos, can you hear me? Can you hear me, Carlos? I cannot hear him.
Okay, now you can. Okay.
Good.
Okay?
Yeah.
Okay. Good.
So, maybe we can start.
Yeah.
So I would like to thank you, all the members of the jury, to come today to listen to the PhD defense of Ninad Manerikar, titled Visual-Inertial Sensor Fusion and State Estimation for the Navigation of Autonomous Vehicles. So I'm Ezio Magis, and I'm the research director at IRIA, and I will be the president of the jury. And I would like to welcome Carlos Silvestre, who is professor at the University of Macau, and he is the main reviewer, and he is connected online with us. On my right, we have Rita Cunha. She is assistant professor and EST Universidad of Lisbon, and she is also a reporter, reviewer. And on my left, we have Liga Marva. He's an R&D engineer at ONERA, and he's also a reviewer. And then we have Tarek, who is Tarek Ahmed, who is professor at the University of Brazil, and he's the research director. And Mindik Iwa, who is a researcher at CNRS, and he's a co-supervisor. Okay, so Nina, you have 45 minutes, and then we will have some questions. I forgot somebody. Sorry.
That's okay.
I forgot because maître de conférence at Lyon, and invited me. I'm sorry.
No problem.
I wrote down your name. So, Nina, you have 45 minutes.
A very good afternoon to all of you. My name is Ninad Manerikar, and today I'll be presenting my thesis topic, that is Visual-Inertial Sensor Fusion for State Estimation for the Navigation of Autonomous Vehicles. This research was carried out at the eProject Laboratory under the supervision of Dr. Manerikar and Professor Tarek Ahmed. Now let's start with the outline of the presentation. So, firstly, I'm going to introduce the topic in a very general manner. Next, I would talk about the motivations which actually led us to studying these problems, because of which we made some contributions during the period of these 3.5 years, especially the design of Riccati observers for the problem of state estimation. Next, I will talk about some of the projects and some of the aspects for the software architecture of all these platforms that you see here. And finally, I'll provide some concluding remarks and some future perspectives. So, what is state estimation? Now, robotics inherently deals with things that move in the real world. We live in an era where we have a rover on Mars. We have drones surveying the Earth, and soon we will have self-driving cars. Now, although these robots have their own subtleties, we must face a common problem in all these applications, that is, state estimation and control. The state of a robot is a set of quantities, such as the position, orientation, velocity, that, if known fully, describe the robot's motion over a period of time. Now, in the context of this thesis, we focus entirely on the problem of estimating the state of the robot. So, what are the various applications of state estimation? The most important one would be to know the pose of the robot, that is, the position and the orientation of the robot with respect to the environment. And with this, we are able to perform a few applications, or many applications like obstacle avoidance, localization and mapping, 3D mapping of the local environment, as well as station keeping. However, in order to perform all these applications, we need some sort of measurements. Where do these measurements come from? These measurements come from various sensors such as cameras, sonars, IMUs, GPS, etc. However, all these sensors have some properties and they cannot be used in all possible scenarios. Some of the sensors do have issues as well. Next, I'm going to talk about some of the issues of these sensors. So, for example, if you talk about a GPS, for instance, if you are in a closed building, you don't have a very reliable GPS signal, or you may even lose the signal. For example, in this room where I'm giving the presentation. Also, inside dense forest, you may not have a GPS signal. And also sometimes you can have interference issues because of GPS sensors. And they are expensive as well. Next, I would like to talk about the acoustic sensors, which are mostly used in underwater applications. Firstly, they are a bit expensive. And second, when you're close to the seabed, the acoustic sensors can often provide unreliable readings. So, what was the objective of the thesis? It was to choose a sensor suite, firstly, that is low cost. Secondly, it should be versatile enough that it can work in all possible scenarios. And we wanted a physical interaction with the environment. So we decided to use the sensor suite where we use a monocular camera and an IMU. Now, a monocular camera is relatively cheap. It gives rich information about the environment and it does so at a relatively high frame rate. With an IMU, you get really important measurements such as the angular velocity, specific acceleration, and the magnetic field as well. So we decided to use the visual-inertial sensor fusion. And one of the important things why we decided to use this also was to avoid using any sensors which provide us with the velocity measurements. Next, I would like to talk about some of the activities that we carry out here in the ETHROSIS laboratory. The members of the ETHROSIS community have been working in various fields of robotics like aerial robotics, and they have worked on VTOLs, fixed wings, hybrid vehicles, where they have developed state estimation algorithms and nonlinear control theories. In the past 5 to 7 years, we have developed 2 in-house robots, one which is fully actuated and the other one which is under-actuated. And these platforms have been used for experimental validation of the state estimation algorithms and the control theories that have been done in the lab. So, the members of the ETHROSIS community have a strong expertise in the fields of visual servo control, the development of nonlinear observers, and developing nonlinear control theories. So, taking all this global picture into account and taking into account the background of the members of ETHROSIS, my PhD focuses on the development of nonlinear observers by fusing data from images and IMUs, whose applications will not only be restricted to a specific domain in robotics, but can be used on any vehicle which comprises of this sensor suite. One of the things we also discussed at the beginning of the PhD was to have a good implementation of all these observers in C++ in the form of a standard library. Therefore, there was a great emphasis on not just the theoretical, but the practical side of things in this PhD. So, the global objective here was to develop state estimation algorithms that can be used as real-time feedback information in control strategies for autonomous vehicles. However, throughout the thesis, we worked under the assumption that the visual target seen by the camera is either planar or nearly planar. Now, many people think that this is a restrictive assumption, but if you look at the various fields in robotics, for instance, underwater robotics, if you want to do the inspection of bridges, or if you want to do the inspection of a shipwreck, the surfaces are planar or nearly planar. In case of aerial vehicles, if you have a drone which is flying over a high distance from the ground, you can say that the observed scene is planar or nearly planar. So I would say this assumption is more application oriented rather than being restrictive. So these were some of the contributions or some of the papers that we published in international conferences. And recently we submitted a journal paper as well. Today, I would like to talk about the three most important contributions, what I feel would be interesting for the members of the jury, as well as for the audience, which are the design of Riccati observers for the estimation of partial attitude, linear velocity, and depth, and the Riccati observer design for homography decomposition. And finally, I would also give some details about the development of the homography lab library. Now, before I move on to the Riccati observers, I would like to give you the vision brick, which we use as the basis for designing these observers. So from this vision brick, we obtain some measurements which will be useful in the design of Riccati observers for state estimation. Now, as you already saw, we work under the assumption that the visual target is planar or nearly planar. Therefore, we exploit one of the classical techniques in computer vision, which is homography. Now, what do you mean by homography? So, any two views, consider these two views of the same planar surface are related to each other by this matrix homography. The homography, it encodes the camera's pose relative to the scene, the position and the orientation, the distance to the plane, and the normal vector. So I'll just show you a video which will help you to understand this concept better. So before starting the video, here we have a camera IMU system, and you choose, how does homography work? You choose the reference image at time t equal to 0. So for us, the reference image is this set of two images. Now, the homography is the homography is computed between the reference image and the current image. I'm sorry for the delay in the video, but over here it's working properly, but there's some problem with the transmission. So it's actually done for real-time stabilization, but I don't know why it's not real-time over here. So the idea is you need to compute the homography between the reference image and the current image. The warped image here gives you an estimate of the quality of the homography estimate. You see here that the reference image is constructed really well, showing how well we obtain the homography estimate. You see here that I even put my hand in front of the target, but we are still able to obtain a reconstruction of this reference image, showing the robustness of this observer. So, in this work, my part was only on the implementation side of the things. So, during the first year, I was working purely as an engineer, and the theoretical work was done by the members of the team, and I was responsible for the real-time implementation of this algorithm. So now that we understood the concept of homography, I'd like to talk about the kinematics of the system. Now, when you have a camera IMU system, the kinematics are given as follows, where H is the associated homography matrix, and the kinematics of H are given by H dot is equal to HU, where U is the group velocity which is induced between the camera, which we saw in the video, and the stationary planar scene. That satisfies the following equation. Now, this group velocity is often referred to as continuous homography in literature. Now, you saw that we have a IMU as well. So, if we are able to extract this omega, which is the angular velocity from the IMUs, we are able to compute two quantities. First is the translational optical flow, which is V over D. So this is done just by simple decomposition. You obtain U, you have the measurements of the gyros, from which you obtain the translational optical flow, V over D, and the optical flow divergence, which is the projection along the normal vector, which is eta transpose V over D. And these two measurements will be further used in the design of Riccati observers, which I will show you in the upcoming slides. Now, I'm going to give you some background of Riccati observers, the Riccati observer design framework basically. There are three properties to Riccati design framework. First order approximation of a class of nonlinear systems, exploitation of the continuous Riccati equation, and exploitation of the uniform observability condition. Now I'm going to explain a bit more of these things and explain the framework which I'll be using to design the observers. So let's consider a class of systems of this form, where X is the observer error system and it is divided into two subsystems, X1 and X2. And X1, it evolves in the closed unit ball in Rn1, and X2 is the error system that evolves directly in Rn. C here is the continuous valued matrix, and the A matrix over here is of the following form. Now, in order to design the observer, we need to apply the input U, which is minus PC transpose Dy, where P here is the symmetric positive delta matrix, which is the solution to the continuous Riccati equation given below as follows. Now, if you have two matrices, this B and this S of D, if they are positive and the pair A star and C star is uniformly observable, then we can say that the observer zero error is locally exponentially stable. And this theorem was proved by Professor Tarek Hamel and Professor Claude Sampson in their paper. And they were the first ones to design this Riccati observer framework. After which, Dr. Minto Khua made a significant contribution in this field as well. And because of which, I was able to apply this framework directly on the problems of state estimation. So let's talk a bit about the observability definitions and conditions. Now, let's consider a linear time varying system of the following form. Such a system is said to be uniformly observable if, from the measurement of its inputs u and the measurement of its inputs y, we are able to reconstruct the initial state of the system. Now, the uniform observability, it depends on the observability grammar defined as follows. Now, the most difficult part in designing an observer is to compute this uniform observability grammar, because in order to compute this grammar, we need to compute the transition matrix phi that is associated to the matrix A of T. Now, in practice, the computation of this transition matrix is not always trivial and can be quite difficult. Therefore, if we can prove we are able to satisfy the condition for the observability grammar, then if this term is positive, the observability grammar, then in certain cases, we can just provide a sufficient condition for uniform observability. And this condition was given by Pascal-Moron, which is determinant of M transpose N should be greater than or equal to mu, where mu is a positive variable. And throughout the remainder of this thesis, we have used these conditions for uniform observability. So this is the first contribution which I've done during this thesis, that is to design the Riccati observers for estimation of partial attitude, linear velocity, and the depth. So what are the challenges that were involved in designing the Riccati observers? First, we know that aerial vehicles, they don't have a sensor that directly measures the linear velocity. In the previous slides, we saw that from a monocular camera, you are able to obtain the optical flow, which is the velocity divided by the distance. Okay, and you're never able to obtain linear velocity. Thus, from a monocular camera, it is very difficult to estimate the depth as well as the linear velocity. And there have been some works in this field in order to estimate these quantities. The standard approach, it relies on applying the extended Kalman filter. However, in these works, they prove experimentally the practical convergence of the errors. In these works, the observability as well as the convergence analysis is either missing or incomplete. Another work was done by Vigraf et al., where they use a deterministic observer approach in order to estimate these states. However, they work under the assumption that the IMU provides the vehicle's linear acceleration expressed in the body fixed frame. However, this assumption is false because the IMU provides the vehicle's specific acceleration expressed in the body fixed frame. Therefore, we decided to revisit this problem, and the objective was to design an observer based on the Riccati design framework, exploiting the fact that the IMU provides the specific acceleration expressed in the body fixed frame. Now let's move on to the design of the observer itself. So, what do we need for design of observers? The first thing is the measurement from the sensors. So we have an IMU which provides us with angular velocity and specific acceleration. We have the monocular camera we saw before, which provides us the translational optical flow and the optical flow divergence. Then we write down the system equations given below as follows, where R is the attitude matrix, V is the linear velocity, and S we define as the inverse of the depth. So what is the objective? The objective is to estimate the partial attitude, that is the roll and pitch angles, linear velocity, and the depth. So how do we now write the general form of the observer? It is simple. You just copy down the system and you add these innovation terms, which are sigma R, sigma V, and sigma S. Now what is the goal of these innovation terms? These innovation terms are proposed or designed such that they guarantee the convergence of the estimated state to the real state, and that is what we want. The next step involves writing down the observer error dynamics of the system. We define the error variables as follows. Yeah, the objective is to make sure that these error variables converge to E3, 0, and 0. Next, as we saw in the Riccati design framework, the step involves first order approximation of the error system and measurement. Here there is one interesting point, that RTIL, that is the attitude error matrix here, it belongs to the SO3 group. So the first order approximation, the elements belonging to this group, is not trivial. We decided to use the Rodriguez formula in order to perform the first order approximation of this matrix RTIL. Specifically, we use the vector part of this unit quaternion Q tilde, and the Rodriguez formula that associates Q tilde with R tilde is given below as follows. And looking at the observer error dynamics, or using these dynamics, we are able to compute lambda tilde, which is nothing but twice the unit vector quaternion associated with this matrix R tilde. Now, the dynamics of E tilde is quite simple because it evolves in the space Rn. So once we perform the first order approximation of this error system and measurement, we obtain a linear time varying system of the following form. Right here, you can see that x1 is the vector part of the matrix R tilde, and x2 contains the two elements S tilde and V tilde that belong to the set Rn. So in the end, what you obtain is a system of the form x dot is ax plus u and y is equal to cx, defining the system output vector as follows. The next step involves designing the innovation terms or computing the expression of the innovation term, which is done by using the input u and is computed as minus pc transpose dy, which I showed you earlier in the Riccati design framework, where p again is the solution to the Riccati equation. Now once you have designed the observer, the next step is to prove the local exponential stability of the observer. And this is what we do. We all know that the local exponential stability of the observer, it relies on the uniform observability of the pair A star and C star. Now the pair A star and C star are computed by setting x equal to 0 in these equations. One of the important contributions in this work which I performed was to explicitly compute this transition matrix phi. And after computing this transition matrix phi, which is the solution to the following equation, we were able to deduce two sufficient conditions or two persistent excitation conditions that guarantee the local exponential stability of the observer. Here, I would like to make a few comments regarding the persistent excitation condition. We see that in the case when the aerial vehicle is stationary, that is V of tau is 0, the persistent excitation condition is violated. And this can be seen in the experimental section, which I'm going to show you in the next slides. So I'll show you the video of the experiment we performed here. So here we use a camera IMU system along with optic rack markers, which are used to obtain the ground truth data. We have a horizontal target plane in order to compute the optical flow and the optical flow divergence. On the left here, you see the blue plots are the ones obtained from the observer we designed, and the ones in red are the plots that we obtained from the ground truth data. So during the period of 0 to 60 seconds, we see that the estimates obtained from our observer, that is the linear velocity, the roll and pitch angles, as well as the inverse of the depth, they converge really well with the ground truth estimates. Now, this is because of the fact that the persistent excitation condition is preserved in this time period. However, if you look a bit further between time period 60 to 70 seconds, we make sure that the camera is stationary, meaning that the persistent excitation condition is violated over here. And to give you a better idea, we can see in this plot that the depth estimate diverges away from the ground truth estimate. But as soon as the persistent excitation condition is revoked again after 70 seconds, that is, we start moving the camera again, we see that the depth estimates start converging to the ground truth estimates. Now I move on to the second contribution of this thesis, that is, I designed Riccati observers for the problem of homography decomposition. Now, what do you mean by homography decomposition? Homography decomposition is the process of decomposing either the Euclidean homography matrix H into its individual components, that is rotation, scale position psi over d, or eta. You can either decompose the Euclidean homography matrix or the inverse of the Euclidean homography matrix in order to obtain these components. Depending on the application, you can choose you want to decompose either the Euclidean homography or the inverse of the Euclidean homography. Next, I want to talk about some of the approaches that are used in order to compute these individual elements. Now, Fogeras and Lussman were the first ones in order to compute these decomposition elements. They used the singular value decomposition where they considered the diagonal matrix to be the homography matrix. However, this method gave each solutions, out of which the correct solution was chosen by taking into account some physical constraints like the reference point visibility, reference plane crossing, etc. But even with these physical constraints, it's very difficult to predict the correct solution. Zhang and Hansen proposed a similar approach where they do the SVD of the matrix H transpose H. Again, you obtain 8 solutions. It's very difficult to choose the correct solution. Then Professor Malis, who is here with us, and his student Vargas, they came up with another approach where they provide analytical expressions of the decomposition elements of the homography matrix. Here, you obtain 4 possible solutions, out of which you can eliminate two solutions by the positive depth constraint. However, again, amongst these two solutions, it's quite difficult to choose the correct solution. So we categorize all these approaches as algebraic approaches. And what are the main drawbacks of these approaches? Firstly, they solve the problem on a frame-by-frame basis, meaning that for each image, they compute the decomposition elements to the associated homography matrix, meaning there is absolutely no filtering. And because of which, the precision of these decomposition elements, it is highly prone to noise, especially for small translations. Or the problem even becomes degenerate when the translation is 0. And in this case, you can have infinity of solutions. And it is very difficult to choose the correct solution. So why did we start off using Riccati observers? So in order to explain that, let's recall the condition of uniform observability. So if you see, sometimes it is possible at some time instance that this term might be 0. But since you have this integral between t to t plus delta over an interval of time, term will be positive. However, for algebraic approaches, as soon as they lose this instantaneous observability, the methods will fail. However, the Riccati methods will still work. So the Riccati observers are iterative methods which give us robustness in a certain way, as well as they give performance because they filter, since it's an iterative method, they provide a sort of filtering on the noise, on the measurement noise actually. So next, I will talk about the actual design of Riccati observers for the problem of the Euclidean homography decomposition. Again, we proceed in a similar manner, where you have the measurements obtained from the onboard sensors. So for us, we have an IMU, provides the angular velocity. You have the monocular camera, which provides us the translational optical flow and the optical flow divergence. And you have the homography matrix H here, the Euclidean homography. You write down the system equations again, and the objective here is to estimate the decomposition elements, which is R, zeta, which is the scale position, and eta, that is the normal vector. Now here we perform one trick before writing down the system observer equations. We perform an over-parameterization of the system here. That is, we replace an element of S2, right, by an element of SO3 group here, that is Q, which is an auxiliary rotation matrix. To keep it short and simple, we do this kind of over-parameterization so that we can write the error system in an elegant manner. So we obtain the observer error form as follows, where we copy down again the system dynamics, but we perform the over-parameterization of the system, and we obtain these variables, which is Q hat, R hat, and zeta hat. And again, we have this innovation terms sigma Q, sigma R, and sigma zeta, which will be designed in the upcoming slides. So I said this, but the procedure for the Riccati observer follows exactly in the same manner. So I'm not going to go again into the details of the error dynamics, performing first order approximation, then obtaining a linear time varying system, and then designing the innovation term. I would directly move on to the observability analysis. We saw that the local exponential stability of this observer, again, it relies on the uniform observability of the pair A star and C star. In this work, however, we were not able to compute the transition matrix. However, we were able to deduce a sufficient condition which satisfies the observability grammar, and because of which we obtain the local exponential stability of the observer. This is the persistent excitation condition that we deduce. Now, let's move on to the experimental validation of this observer with respect to the state-of-the-art algebraic approaches. So I would like to show you this video in order to present the experimental setup that we use. So here we have a camera IMU system, again with OptiTrack markers. And here you see the real-time performance of the observers. So I would like to go next into the plots to give some remarks. So we did a comparison between three methods here. The method 2, with the plots in red, are the estimates of the observer we proposed. The method 3 in green is the algebraic method proposed by Matisse and his student Vargas. And the plots in blue are the ones that we obtained from the ground truth data. So it is clearly seen that the algebraic method, it gives relatively good estimates of the scaled position and the attitude, as long as there is a sufficiently large translational motion. But when the translational motion is small or it is close to zero, that is the regenerate case, it gives erroneous estimates. And this behavior is clearly highlighted between the time period 195 to 225 seconds. So here you have really small translations, but you can see the erroneous estimates provided by the algebraic method. And this can be explained because of the fact that amongst the 4 possible solutions obtained from the algebraic method, the choice of the correct solution depends highly on the precision of the normal vector. But the normal vector proposed by the algebraic method is prone to noise, and in a degenerate case, it gives erroneous estimates. In contrast, if you look at the observer we proposed, we get relatively good estimates for the state position, the attitude, and the normal vector, even in such a degenerate case, showing the performance of the observer or the advantages of using this approach over state-of-the-art algebraic approaches. Next, I would like to talk about the development of the homography lab library, which we implemented, which was one of the main objectives of the thesis as well. That is to do a practical implementation of all these observers that I showed you before. So all these observers are part of this library. We started off with a simple embedded computer, which was an Odroid XO4. So we started off with a simple CPU implementation. The objective was to make sure that the algorithms run in real time. Next, we tested all these algorithms over various NVIDIA GPUs actually. So we tested it over the Jetson Nano, Jetson AGX, Xavier NX, and we performed even the GPU implementation of this homography lab library. One of the important things was to make sure that this library was written purely in C++ so that we can do an optimization of the code as well. This library was evaluated at TRL 8, where TRL stands for the technological readiness level and is protected by the French APP. And this library has been used for performing experimental validation of all the developed theories. I already showed you the video of image stabilization. In the upcoming slides, I'll show you how we use this library in order to do station keeping of an EUV. And lastly, for state estimation. So during the period of my PhD, I've worked on several projects. The first one was a 3-year project, the Green Explorer project, and it was a joint venture between IIIS, the University of Toulon, and Alcimar and COMEX were 2 industrial partners actually, which are close to Marseille. So Alcimar is in Aix-en-Provence and COMEX in Marseille. And here, I was responsible for the complete integration of the software into the Alcimar architecture, where the company Alcimar was responsible for completely developing this vehicle. The vehicle concept is fully actuated and has a downward-looking camera. And the idea here was to use the homography lab library to perform the dynamic stabilization of this vehicle. Just like to show you a video here of the experiments we performed. So here, the idea was to perform the dynamic stabilization of this vehicle over the target here. You can see here that the target is not exactly planar. you have a downward looking camera, and here we exploit the homography decomposition observer in order to obtain the force which is sent as a feedback information to the control loop. And then using control, we perform the dynamic stabilization of this vehicle. And that's what you notice over here. This experiment was carried out in the pool in the company Comex. And next, they also performed the experiment in real world conditions where they went to the sea close to Marseille to perform the dynamic stabilization of this vehicle over this target, which is again not planar. It's basically seaweed, and the algorithm works really well. So this was one of the projects worked on. The next project was quite important and interesting as well. So, which was the industrial transfer of this homography lab library to ICA Robotics. Now, ICA Robotics is one of the biggest companies for marine applications in France. And again, the idea here was to do a dynamic stabilization, but of an under-actuated vehicle in front of an horizontal target. Here again, I was responsible for the transfer of the library, complete software integration, and what I also did additionally was we had control programs. So I converted all these programs into an Ethros control library, which is similar to the homography lab library. Again, like to show you the video, the experiments we performed with. So this is a prototype of the vehicle that is used by the company. So it has a Pixop, which is an autopilot, it has a pressure sensor and a forward-looking camera. And we use the Jetson NX here for doing the onboard processing. So you can see here that the vehicle is doing stabilization in front of a target. It's the horizontal target here. And here again, we use the homography decomposition observer to compute the elements and send it as a feedback information to the control loop. Now you can see here that the vehicle is making these movements like a car actually. So this is the transverse function control approach that has been again developed by Claude Samson, who is one of the members of the team as well. And you can see that even for perturbations, it does these movements and it tries to come back to the reference position, as you see over here. Next, the other project. Well, I was partially involved in this project. Simone, the other postdoc who was working full-time on this project, where the idea was to land the drone on a moving target over here. So I helped him in the implementation of the vision part. So the idea here was to make sure that the drone follows this target. And you can see here that we perform actually this experiment outside in the parking lot at Ethros. Sorry, there's some problem with the video, there's a lag. So again, you can see here that the drone follows the target quite well. So this was done here so you can see that when I move the target up and down, the drone follows it quite well. Next, Simone put this target on a cart and we saw that he's moving the cart and the drone is following the target over here. And then once we give the command, the drone will land. Sorry for these videos. Then we went outdoor and then performed the same experiments. But here there was quite a bit of wind and we were still able to land the drone on this moving target. So next I would like to talk about the software architecture of the whole system actually. So the software architecture is similar for all these vehicles actually. There's just a slight difference. So we have two underwater vehicles which we use for the validation. Then we have an aerial drone over here. So the box in green here, it is the embedded PC. It performs two processes. First is the vision part and second is the control part. So we have two processes running in parallel where the vision is used for the homography and the homography decomposition, and we send information of these elements to the control node over here. Here, we use the ROS operating system in order to do the communication between these two ROS nodes. And again, we have a camera which is connected to, here we have used a Jetson NX, an NVIDIA GPU to perform all these computations. And you have the Pixar, which has an inbuilt IMU. So these are the three most important things that we have used. And this node basically uses all the functions inside the homography lab library. Once we have, so from the control, you generate the force and the torques, and you send it to the Pixar, which generate the PWM commands, and these are the commands which are sent to the motors. So this is the generic software architecture that we have developed here in the lab. Now, I move on to the conclusions. 2 minutes. So we have addressed many problems related to the estimation and navigation of autonomous vehicles, such as specifically the design of Riccati observers for various state estimation problems, such as the estimation of linear velocity, depth, and the problem of homography decomposition. We used a suite of low-cost sensors, and we were able to achieve good performance even with the low-cost sensors. And we were able to develop the homography lab library for successfully demonstrating the developed theories and the concepts. I would like to talk about some of the perspectives. That is, we have not considered the accelerometer bias in the design of the observers, especially for the one of linear velocity estimation. One of the works would be to incorporate this accelerometer bias in the design. Secondly, is to combine directly the point correspondences for the estimation of the relative force and the normal vector, and use epipolar constraints for treating the case of more complex 3D targets. Thank you all for listening, and open for questions.
So we can start with the questions. So maybe Professor Pharmacy Best would like to start.
Yes, thank you. Firstly, I would like to thank you for the opportunity of being here. Unfortunately, very far from France, but okay. And it was a pleasure to read that thesis, and I found the implementation working correctly, and results are quite good. And I have a couple of questions that I would like to discuss with the candidates.
Yes.
Okay, let's see here. As I told you, for me it was very impressive the results. How the observers that you proposed work quite well, and the real-time implementation that was done in the NVIDIA course, which are quite valuable in terms of in terms of the application that this kind of work can have in the future. For me, I would like you to clarify which are in chapters 3 and 4 your main contributions when you compare to the state of the art. Okay?
Yeah.
Because it was not clear for me after reading it. I'm not telling you that it's not clear in the thesis. That it's quite dense and it was not clear to after reading what was your contribution when compared to the previous work. Please clarify this along the different chapters.
Okay, for chapters 3 and 4, you said, right?
Okay. Yeah.
Okay. So, I go. Chapter 3 was for Riccati, the Riccati or the homography. Sorry. Right. Or cellular aussi. Donc, I'll start off with the fourth chapter.
Yeah.
Okay. So as I showed you here, with the pointer. So I would say for me the most important contribution was that we were able to perform an extensive observability analysis of the whole system actually. And that is one of the points why we decided to use the Riccati observers as well. Another, because in most of these works, which I told you actually, they only prove experimentally the practical convergence of the errors. And that's what the analysis is either missing or incomplete. And in this work, they use a completely wrong assumption, or I wouldn't say complete, it's a false assumption. And that's why we decided to use these Riccati observer design framework in order to estimate these quantities of partial attitude, linear velocity, and depth. Also, one of the things was that we wanted to use a sensor suite which does not directly give the measurements for the linear velocity. That's why we used a monocular camera and an IMU, which, I mean, it's not really easy to estimate this quantity using just a monocular camera and an IMU. And then the whole idea was to do a thorough analysis, and one of the most difficult tasks was to compute this transition matrix as well actually, which helped us to deduce the persistent conditions for the local exponential stability of the observer. So for me, these were the most important contributions with respect to the state-of-the-art approaches that already exist. And then also performing the experimental validation with a real system, a real camera IMU system. So these, for me, in this chapter, were the most important contributions with respect to the state-of-the-art approaches.
Okay. And this was for, I have another question, which is, you use specific acceleration measurements, right?
Yes.
Hello? You are using in your observers the specific acceleration measurement.
Yes. Which is
provided by the IMU, right?
Yeah, provided by the accelerometer. Yeah.
Okay. But your vehicle, they move so slowly that what you get mostly is the gravity and noise, right?
Yes.
How do you think, which is the impact of the accelerometer noise on your on the overall feedback on the performance of the filter? As for looking into the filter structure, the acceleration works like an input, right? To your filter. Okay.
Sorry, can you repeat,
and then
please?
How do you, looking into the structure of your filter, the acceleration is the specific acceleration is one input of the filter, right?
Yes.
And the estimates are driven. Actually, it is one of the terms that drive the that drives the V dot is the specific acceleration. Okay, but in most of your, I guess in all of your experiments, the acceleration is just the gravity, because your drones, they move so slowly that what you get from the out of the IMU, at least if you don't want to spend a very large amount of money, is just the gravity. What is your opinion regarding this?
I'm sorry, but I did not get the question. Like, can you?
The question is that given the kind of application that you are looking into,
Yes.
the specific acceleration is basically equal to the gravity, right? Okay.
Um, not
Hola.
exactly. No.
Okay, hola.
No.
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 If you integrate the acceleration during 1 minute, what do you get? 0 probably, or 10 seconds. Because your vehicle, they do not move very much, right?
Yeah, when the persistent excitation condition is violated. But for the rest of the I mean, if you look at the video where just a second. So here, if you look at the video, we are doing aggressive maneuvers actually. So we are moving the vehicle over the plane actually, over the horizontal target. So here.
Yes.
Yes.
But I don't think you can get this kind of movement out of the double integration of the kilometer. Because taking into account the error in your rotation matrices, the error, I don't think you can get this out of the measurements of the acceleration provided by MU. I guess you are getting mostly the gravity vector. Yeah, the gravity direction. Now, of course, this has impact on your observability a lot because it's a very strong vector, of course.
Yes.
But what I'm saying is that maybe if you assume that you don't have acceleration, or if your acceleration is very small, maybe you can look at the problem in a different way. What is your opinion? Actually, because you can almost neglect the effect of the acceleration, but the one due to the gravity, I guess.
I think in this case,
What is the impact on the observability? It's mostly due to the to gravity, or you really need to have the acceleration to have the full observability of the system, the uniform observability of the system.
and we need to have the acceleration actually in order to have the full uniform observability because we are we are moving the drone in all the directions actually. I don't know if I answered it correctly or not.
You answered, but I don't agree with you. I think that maybe because your vehicle they move so slowly, okay, that you cannot distinguish between the acceleration you have. The acceleration you have, they are much smaller than the noise that you get from the sensor, I guess. At least for the applications you have. So where you move, or of course, if you are talking about very high solution vehicles like aircraft or missiles or so, then it's different. But in this kind of application, maybe. I understand you need to. Yes.
In order to perform aggressive maneuvers, actually, when you perform aggressive maneuvers, you have the specific acceleration as well.
Yes, if you want to perform very aggressive maneuvers, yes, you need to think with that. What my question is, if what we get from the accelerometer it's good, or it's just not. You understand what I mean? Okay. And this, do you think that, yeah, but do you think you can change a little bit your computation in order to, for this kind of application with very slow motion, or maybe it's too hard to do it in another way? When the noise level of your signal are much larger than the natural signal that we take the sensor. Because for the specific acceleration, to get the velocity, the derivative of the velocity, you have to subtract the gravity vector rotated. And this rotation matrix has errors. Okay, and the noise level of your acceleration is quite high. Therefore, maybe this is what I would like you to discuss. If it is possible to look into the filters in another way for this particular case where you have your applications actually.
So you didn't really get
You don't understand my question. Okay. Just a moment. If you look into in equation 40, in page 49, you have this all over the thesis. The acceleration of A of beta plus G R estimated transpose E3. Okay? And what I might say is that maybe this is just zero.
Sorry, in which slide?
What? In page 49.
The thesis.
Maybe do you have the structure of the observer? Maybe a graph?
Yes.
16
Yes, here. You have.
Yeah.
No. In the previous one, maybe. Yes.
over there.
Yes, here.
Yeah.
System equation.
Yeah.
What I'm saying is that in system equation, I'm not saying that this is possible. Just in system equation, what you get is the A of beta acceleration. It's very close to the term.
The gravity direction.
Basically, what you have here is just the gravity dominates completely, and the A of beta is just this term, I guess. Yes, I think so. Do you need this input for the observability is not enough just to rotate the velocity. If you don't see this now, don't worry. You can think about this later. It's just a kind of simplification that could be somewhere, okay? Because you are not, what you have basically just omega cross times v. When you move, you have omega cross times v dominates completely, because the other term, unless you have very aggressive maneuver, it's zero, or it's noise, or in the worst case, it's just noise, which is even worse. Okay, because not accelerometer, the noise level of the acceleration is higher than the kind of signals you have. Most of our applications of underwater or quad rotor, where vehicles, they don't move fast, they don't do aggressive maneuvers in general. This is what I would like to, but maybe you can looking into this, you can see something here, okay? Because I guess what is most important here is just the rotation of the velocity. Okay, but don't worry about this now. We can think about it later. Okay, regarding the implementation, can you describe a little bit what you did? Are you using the cores of the NVIDIA to implement the vision? What you did in terms of implementation? How do you implemented the observer? And then you implemented well. You implemented in real time. You have excellent results. But this is out of question. Just I would like you to clarify a little bit more.
Yeah, so on the NVIDIA, let's say on the GPU, we implemented like a continuous discrete version of this observer actually. And the idea here was to take the inputs from the camera and the IMU. So here we have the camera, which is running at, like some of the cameras which were running are around like between 20 to, let's say, 30 hertz, the frequency. And then we have the IMU readings, which are running at a very high frequency, around 200 hertz. So what we do is we basically use these IMU readings in order to compute like a prediction of the homography, for instance, from which, and then we obtain the homography estimates, from which we deduce the optical flow, the translational optical flow, and the optical flow the optical flow divergence. And then these measurements we provide to the observer, which I showed you before, which is, I mean, the Riccati observer over here actually, where we compute the matrices, I mean, A, C, and the solution to the Riccati, where we compute then the innovation terms.
Okay, but this kind of the observers, they don't require a lot of computation. What requires a lot of computation is the image processing, right?
Yeah, exactly.
Yeah, the homography. Yeah. Did you develop code to running GPU, or you used the
the
code
GPU
already available?
No, I developed the code in GPU using the OpenCV library. So we have OpenCV in which you have the GPU functions for actually doing performance, doing the calculation of the feature extraction and matching. So this is what is the most computationally expensive part actually of designing the observer. So, and that's what.
And the nano enough to do this? So you have to use the Chevier to perform.
No, with the nano as well, we were able to run it around 20 to 25 hertz actually.
Okay, so and how many pixels the image?
So we had around
How
400.
many? Which kind of resolution?
The resolution we chose was a VGA actually, 640 480. But even for an HD image like 720p, we were able to obtain 20 hertz. So for a VGA image, actually we went up to 25 hertz.
Okay, and in your structure, basically you had the GPU running the image processing, and then on the Chevier on the nano board, you compute these small computations you need to do for the filter. Basically, was that, or you had to migrate some of the observers as well to the GPU?
Yeah.
Did you migrate some of the observer computations to the GPU, or you didn't need to do that?
No, for that part, I did not need to do it on the GPU because just using a CPU, it was sufficient. So the major computational cost was the homography estimation actually. For the rest of the observers, it is quite fast because it's just matrix multiplication and performing operations on matrices. So I didn't really need to get into the GPU implementation of these things. But the most important was for the homography.
Okay.
So I mean,
I think I don't have any other. Okay. You clarify my question. Okay, and I congratulate you for the results that you obtained. They are quite impressive. And I don't have any other questions. I'm okay for now.
Okay, so maybe you can go forward with Professor Cunha. Do you have a question?
Okay, first of all, I'd like to greet the other members of the jury and thank the supervisors for inviting me to be here and be part of this committee, and also greet the candidate Nas and wish him luck for the small part that is still left.
Yeah, exactly. Yeah.
Okay.
I need to think about that.
So I appreciated a lot your work and the thesis and also this presentation that you did. I think that you presented a very cohesive and relevant study for state estimation, focusing on this minimal sensor suite, right? It's low cost and it's very popular.
Yeah.
Just a monocular camera and an IMU. And in addition to that, you consider the planar targets, feature-rich planar targets, but I see that in the end you also apply it to not so planar targets, and it still performs quite well. And most of the work was based on using the framework of the deterministic Riccati observers to obtain all these different filters observers. And so my first question was, I read through the thesis, each chapter, and it was always a variation of the theme. So you start with some sensors, like you put on here. It's a good example, right? You take different measurements and then you define your system equations, and there's always not exactly the same in all of them.
Okay.
So I would like you to discuss a little bit from chapter to chapter, or from filter from one to the other. What are the differences? What was the motivation from going from one to the other? If you can discuss a little bit there.
Yeah. So when I started working here, the first year I was working as an engineer. So by that time, they had already proposed the homography observer.
Okay.
But it was implemented in MATLAB at that time. And the idea was to have this in C++ actually, and to have a real-time implementation of this observer. So that was the first thing which I did, was to do the real-time implementation. And from there, actually, the whole thesis started. Now, in the chapter for the Riccati observers, actually, I mean, the whole idea was to exploit this homography estimation in all of the design of these observers, actually. So that's why the basis was always, or let's say the vision brick was always the estimation of homography. And since we use a monocular camera, and also we have we take the assumption that the target is planar or nearly planar. So we did, I mean, this was one of the motivations as well, actually. Secondly, we always wanted to design observers which did not give the measurements of linear velocity, actually. So if you look at the Riccati observer for linear velocity depth estimation, we can use this as a sensor itself to estimate the linear velocity. So, for example, in underwater cases, so you have the DVL, which is quite expensive actually, and it's quite bulky as well. So, if we are able to replace it with a sensor like this, or even for an aerial vehicle, for instance, if we are able to have a sensor which comprises of an IMU and a camera, this could be really interesting as well. So, one of the motivations was, I mean, this sensor suite can be seen as a single sensor itself actually, which exploits measurements from two different sensors. In the end, it estimates various states. So this was, I would say, the main motivation actually, and it's quite difficult as well to estimate from a monocular camera these quantities. So this was the one of the major motivations. For the chapter of homography decomposition, again, it was similar, that we can always work without having linear velocity measurements. So again, it was the same motivation in that chapter as well. The idea was also to develop something generic. So in all these cases, what we always need is just the homography, monocular camera, and an IMU. We don't need any other sensors in order to do these estimations. And for the applications we developed, we have a physical interaction with the environment. So for us, it did not make sense to use an expensive sonar or a DVL, which does not work really well. For us, it's sufficient just to have a monocular camera actually and an IMU. So if using something simple, we are able to achieve something. Did not want to go into something which costs a lot.
So there's one step over there that I think that is missing. You say that you have these measurements from how do you get the translational optical flow, and actually you put in there the homography, but then when we look at the filter itself or the observer itself, the homography doesn't show up, right?
Yeah.
It's an intermediate step, isn't
yes,
it?
It's an intermediate step.
Okay. So
in order to compute the continuous homography, I have a slide on that. I did not put it.
Maybe before?
Yeah, it was just here. So the continuous homography, so the Euclidean homography, you compute between the reference image and the current image.
Mm-hmm.
Whereas the continuous homography, you compute between two consecutive images. Now the kinematics of the homography, as you saw, is h dot is equal to hu. So the u, you can compute just by inversing h inverse h dot. And then you can approximately compute it via the logarithmic operator here, which is where t is the frequency of the camera. Once you have this quantity, you have the omega coming from the zeros. So just by doing a simple decomposition where you can extract the angular velocity measurements, you are able to decompose this into two components, which is the translational optical flow and the optical flow divergence. And so this is nothing but the projection along the normal vector, the translation of the flow.
Okay, so that actually brings me to a question. I was when reading your chapter 3, if you remember.
Yeah.
I got the impression at some point that there was a chicken and egg problem. That
Okay.
you used U to estimate H, and then you used H to estimate U, and I was a little bit confused about it. At some point, you have I don't know, a proposition or something saying that assuming that U is available, then we can get an estimate of H.
Yeah.
And then you used the homography or the
Yeah, because these are two different things. So
Okay.
in homography, so U is the group velocity, which is composed of two things. So you have the angular velocity and you have your linear velocity. So the angular velocity you directly get from the zeros actually. But for the linear or for the second part, you may not have it actually. So we assume that we have this we assume that it is constant, this term,
Okay.
and that's why we do a high gain observer actually, which is basically we do multiple iterations for the correction step.
I see. So maybe you should write it down.
Yeah,
Otherwise
sure.
It's not completely clear. That's fine.
Okay.
Another small comment. When you, even in chapter 2, when you present the Vicati observer, this deterministic Vicati observer, the first time, and you have it there also in the slides. This is just a small comment, but I think that it will help when people are reading the work.
Yeah.
Right.
Yeah, it's right
One
at
of the first slides. Yeah.
Theoretical recursion.
Maybe. Yeah. It could be over here. So you have this small label saying that X is the observer error system. I would call it observer error state or something like that.
Yeah.
But for people that are familiar with observers, I would present this in a different way, maybe with X and X hat. You have the state, you have the state estimate, and then you have X tilde, and everything becomes more clearer, and we can,
I could have, sure. Could have
Because
simplified things
even-
more,
yeah,
and it would have been easily understandable.
Yeah, I only got that when I read over, when I moved over to chapter 4, what we were talking about. And even there, you have the A matrix over there, and it depends on X hat, and we get confused. What is X hat? Is it the estimate of the error? So, this is just a small comment.
I should have.
Another question is related to what you talked in the end. You talk about considering bias in the measurements, but you only talk about the accelerometers, and I would say that we always consider bias when you talk about gyroscopes. And here, that
But
problem.
for
So
gyroscopes, you can
you
actually.
assume that it's calibrated.
I mean, it's slightly more easier with the gyroscopes because you can actually keep it on a table actually, and you can try to do a good calibration of the zeros actually.
Okay, but
Whereas for
it's
accelerometers,
a little bit time varying,
Yes,
as you progress in your experiments, then probably you have to stop and calibrate again.
Could be. Yeah.
The other approach would be, to include that.
So we could have the estimate for both the bias on the zeros as well as on the accelerometer actually.
Would it be very difficult to incorporate that in the structure of the observer?
I don't think so. No.
Maybe we to change
change the structure of the observer, but I don't think so. It would be too difficult to incorporate these measurements into. Yeah. So, no, actually, the observer would remain the same. Actually, it would just we'll have to estimate the biases separately, and addition of few terms in the wouldn't be the same, but few additional terms.
maybe you won't like it, but I will pick up a little bit on the question
Yeah,
from
sure.
Professor Carlos about the accelerometers.
Yeah.
And when we think about the classical structure of just an observer for orientation, for attitude observer, the common filter gives us for free a little bit of a complementary filter structure, where we have for low frequency, we are using the accelerometers. For the high frequency, we are using the gyros, and this combined gives us a good estimator for the attitude. Can you see in your observers some kind of frequency domain interpretation of what you're getting? This is a hard one.
Sorry, let me just go back to the. Yeah. I need to think about this actually.
Okay. A question about the experiments and simulation and experiments.
Yeah.
You compare to ground truth. So you have a motion capture system, and you compare the results. But you talk about other, apart from where you get to the comparison with the algebraic solutions.
Yeah.
Did you try any kind of other filters? Just an extended common filter. How would this perform? What? So that we can, see the distinctive features of this.
So, the Riccati design framework is basically an extension, or is similar to a multiplicative extended Kalman filter actually. In an extended Kalman filter, what you typically do is you linearize the system around the trajectory. But you don't know the trajectory. What you do with the Riccati design framework is that you linearize the system around an equilibrium, around an error, and you prove that it is identity or close to zero actually. So this, I would say, is the major difference between using either an extended Kalman filter and the Riccati observer design framework. But I would say the biggest advantage is that we are able to do a thorough analysis of the observability conditions. We are able to achieve, or we are able to compute these sufficient conditions actually, which guarantee the local exponential stability of the observer, making them, I would say, more robust. So I never did a comparison, but I read through some of the words. But yeah, it could be interesting to at least see it. From the practical side of things as well. Because I always talk about the observability analysis, but it would be nice to do an experimental validation with two observers, like an extended Kalman filter and a Riccati observer, to see in the implementation part as well, if we are able to achieve similar results, or what are the
So you present results as usual, right?
Yeah.
That work. But from your experience when actually implementing and testing the observers, I guess that in the beginning it didn't work, it diverged, or some. Can you talk about that part of your work?
The most difficult, I would say, is to tune the gains of these observers as well, actually. Especially the matrices B and S, actually, of the Riccati.
Yes, exactly. So how do you choose them?
Oh, so different.
And
it was
funny. It was just a side comment. When I read your thesis, you present. I think you present a Riccati equation somewhere, and all the matrices you omit the dependence of time, except on these two matrices. It seems like everything else is, well, although you have an LTV system, it doesn't matter. It's only those two that are time dependent.
Because for me, I think so the most difficult part was actually in all these experimental validations was to tune the gains of these two matrices actually, D and S, which are very sensitive because depends on these matrices also incorporate the like for the angular velocities, the convergence of the rotation matrix actually. So these incorporate all the gains actually. So these are like the various covariance matrices of the Kalman filter. So you get a bit of hint actually the way you from designing the Kalman filter as to how you can design these gains as well. But there were many times where I had to sometimes do a trial and error actually. So you know approximately the values, but some instances I had to sit a bit and
I think that's reasonable. To think of them, they don't have to be they don't have to come from the specifications of the sensors. You can look at these matrices as tuning parameters for the observer. Okay. I had a question just about the last part. Something that was not clear to me in the thesis, which was, did you actually use your observers to control the system, so close the whole loop? But I see that
this is,
in the end
I
you
think I
showed a
wasn't
lot
clear
of
in this.
Yeah.
The homography observer, which is done for the estimation, has been done by other members of the team. I was responsible only for the implementation part. But from the homography observer, the homography decomposition observer, which I showed you, so that is my work, and that is a part of the homography library as well as all the other observers. So it's only the homography observer, which is not what I have done. I have just done the practical implementation of that observer. But the remaining, they have been used in the control loop actually. For example, the homography. So in order to perform the dynamic stabilization of the vehicle, we did use the homography decomposition observer. And the elements we obtained from that were sent as feedback information to the control loop. Okay. And this control loop exploits this observer, and then we perform the dynamic stabilization.
In that case, was the system satisfying those persistent of excitation conditions? Because you're stabilizing the system.
So there was in the homography decomposition observer, I said that the normal vector actually should always be pointing downwards, but in actual experiments, what we performed, you see that we can specify a certain cone actually because the direction of the camera is exactly the same as the E3 vector. But when we performed experiments, we saw that it doesn't need to be the case exactly, and it's impossible to have this condition at the beginning where eta 0 is exactly equal to, let's say, the E3 actually. So even we performed experiments with the underwater vehicle, and you can see that it's not the same, but it works. I think we even performed experiments where we had an error of around 30 degrees, and it works in these conditions.
I had almost finished, I think. Just a small question about the service that you propose in chapter 5. You have one for estimating the homography and then another one for the inverse homography.
Yeah.
Why do you have these two, and what are the differences? What is the advantage of one over the other?
So depending on the application actually, what do you want? So if you see here, the D0 is the distance from the reference frame actually, and eta 0 is the normal vector. So at this point, these quantities so you estimate these quantities with respect to the starting position actually. So there are certain cases where you would require these quantities, but in other conditions you would want to have these quantities. So the design of the observers remains exactly the same, but what changes is the measurement actually. So for instance, we use this the decomposition of the inverse actually in order to perform all our the experiments as well. So even for, let's say, an anti-collision actually. So we can use these parameters for those functionalities.
Okay, just to wrap up.
Yeah.
If you can tell us, you've said it already more or less, but what would you say is the biggest contribution of your work, or what was the stepping stone where you said, okay, my PhD is done, I can go forward and have my defense?
For me, it was a bit of both, like the design of Riccati observers actually, where there was a lot of computation involved, and I was really happy the fact that they could actually develop a library which has been used by industries as well. I mean, so I was really happy about that fact that, I mean, it's not just all the theory what we do. I mean, it is extremely important because without that, you cannot achieve the results what we have done. So I was really satisfied with the implementation aspects as well because, and we have for the library, we have the TRL 8 and the maximum you can achieve is TRL 9. So we are in a stage where we are almost there actually. So and I hope that maybe in the next year we will reach TRL 9. And, I mean, let's see. So that, I think for me that was quite important as well to do an industrial transfer of the work what is going on in the lab to companies. So for me that was quite satisfying, and I really enjoyed working on these different projects actually. For me, the most satisfying thing is to see everything working on the platforms actually. So what you do in the lab and then what you see when it works, there's a kind of satisfaction what you have. So, yeah.
Okay, thank you.
Thank you. So now, maybe Julia has some question for you.
Yeah.
Thank you. So yeah, also thanks for inviting me. Yes. Yeah. So I read your manuscript, your report. So the manuscript was good, easy to read, quite structured. So globally, it's a good manuscript. You have my comments in the report.
Yeah.
If you want, if some of them can make their way to the final version, maybe.
No, of course, yeah. No, I really appreciate, especially the last part for the phrasing. There was.
Yeah. So yeah, one of the chapter, I was happy with the context, and it was also very clear in your presentation. The big picture was clear motivation. Okay, the setup is given in the beginning. There's nothing wrong here. It's good. The developments, okay, were in the line of the lab somehow. Nice. A lot of applications. Okay. We understand well what is the contributions. What I was not very happy with in the manuscript was the implementation chapter, because you instead a lot of an application practical side, and it was a very small chapter, which somehow was not very well related to the rest, because it talked about AUV underwater application, while in the previous chapters you had more aerial or hand sensors, and there was some of a gap here, but today you've shown some more things here that were not in the manuscript, with underwater experiments, which worked, with the transfer stuff, etc., which somehow bring more elements on this part. So somehow you answered here, but maybe you can also add this in the manuscript to make it more consistent. So
okay.
That's more to help you
take that in.
To criticize. Okay, so. Do I have remaining questions with what has already been answered? Yes, I have. Sorry for that. Yeah, I was not very happy with your justification of the planar assumption. So I know, yeah, when everybody is doing, when someone is doing homography, it's easy to say, hey, come on, everything is not planar. But this is not what I'm getting at. You said that in the real world, somehow, the applications turn out to be planar. You said something like that at the beginning. That it's not a big deal because what we studied and what we applied was okay with what we are doing. But yeah, we were stabilizing stuff, so of course it is. So actually, I think it's a good point to, but it's not a big problem to have an assumption for your method. All the methods of the world have assumptions. But my question is then, don't you think it's better if you can detect if your assumption is wrong at some point and then adapt to it? Or do you really need to have this assumption in your method? So can you somehow find through your filters or in your loop when the assumption is not valid, and can you do something to adapt when it is not?
I mean, for me, we would then move on to the perspective section where we said that we also try to do this for 3D targets actually. So the thing is, if the homography does not work, so if you lose it at some instance, then you lose all the measurements as well actually. So in that case, we will have to look at it in a different way. The way we design the filter as well. So one of the next steps actually is to not remove this assumption completely, but also to try to work with 3D targets, still using homography, but using epipolar constraints actually, where we can treat the case of 3D targets as well actually. So you do use homography, but you use a patch which is kind of planar. So if you have like a circular or a semicircle, let's say, then you can take a patch of it, you can do the homography. Around that patch, you can use these epipolar constraints as well in order to create this kind of 3D structure. And
okay. So yeah,
so
you
this
will
is,
want to improve the method
so
rather
this is one of
than
the
changing the method.
Yeah, this is one of the future perspectives actually, or this is one of the future works as well.
Okay, understood. I also have to say something on slide 16, 17. I'm sorry. A lot have already been asked, but I have one more on this. It's working a lot. Okay, so basically, one of your motivation and justification for using dynamic frequency observer was that you are getting a synthetic stability and you are able to perform a quite thorough observability analysis. And of course, yes, I agree, this is a very interesting point and useful point. And this cannot be done with an extended camera filter. If you go to the next one, in the end, in your filter, it doesn't okay, you have not done uncertainty propagation. This is a deterministic observer. Somehow you have no need for uncertainty assumptions on your inputs. And you have a lot of measurement inputs here. And you are doing sensor fusion there. It's
a sensor fusion.
And you're putting a lot of stuff together. And in the end, you have an output which asymptotically converges to what you want, but with unknown uncertainty. So what disturbs me, and the camera filter can analyze this at a certain level because you are linearizing and so on, but you can quantify the impact of the uncertainty, the covariance you have on your inputs. You can propagate it in the filter and get it on the output or the state estimation. Can you do it here? could you do it here? It's beyond your scope, huh? Don't worry,
Yeah,
it's just
yeah.
a question.
This is an interesting question.
I mean, you have noise on the flow, you have noise on the gyros, everything has noise. And
Yeah, but since it's an iterative method, it already is kind of a filter on the measurements actually.
yeah, but you cannot filter out everything. There's always.
This I need to.
Okay, so you didn't study it.
Yeah, I haven't studied that yet.
All right, and then related to this, your inputs are at different places, so it's quite common in sensor fusion to have them in the input and in the correction outputs. But here somehow some of the estimates and the inputs find their way into the matrices. In A, you've got the flow, if I'm not mistaken. Yeah. You got 5 here. Also the gyros. Okay. You're okay with this? But this is part of the method.
Because this is the part of the framework. So if I go back to the slide.
I think it's because this is a narrow system and so on. But
Here is the form of the system actually. So the matrices, what you obtain over there, the A matrix, for instance.
It's consistent with your.
Yeah. So.
Okay. But still it's disturbing from a propagation function. Okay. All right. Yeah. Another question which is beyond your scope, beyond what you have done. So motivation to use the camera alignment system was that it is cheap compared to all the stuff, or the more expensive stuff that you have. Okay. You said you cannot use linear velocity sensors because they are expensive or they are not appropriate to what we are doing with the robotics. Okay. But now today you have some very cheap range sensors. Somehow. Time of flight sensors or contrast LiDAR, small sensors, which fall into the category of cheap sensors. So somehow, and if you have a planar assumption, getting back to this, and you are pointing some lasers to it, somehow you have depth measurements. So
yes, it's
distance measurements.
Yeah.
Okay. So my question is, if you add this in your framework, does it help you?
I mean, so it would just change slightly the structure of the observer, where I need to add an additional measurement into here. But it depends on the noise, or depends on the noise of the measurements provided by these sensors as well, actually. So, I mean, I'll have to.
Is it possible to take them into account?
Yeah.
Okay.
Because it's just an additional measurement so if you add a sensor, what you typically, you obtain another measurement, which can be incorporated into the system. So here when we estimate depth actually, so you can incorporate the measurement of the depth. But I'm not sure if the measurement will actually help the estimation of other quantities or not.
By somehow you have a direct guess and measurement.
Yeah.
So it will have convergence. Okay, I agree with you. You have to study, but okay, you say that it's possible. I'm okay with that. And yeah, one last is for the continuous homography estimation. You didn't give a lot of chance to the algebraic method. I mean, okay, it has some jumps because of one part comes from the excitation part. Okay, this is really inherent to the method where you have some ambiguities and so the estimation might get wrong, okay? But on the time smoothing, don't you think that just taking the input of an algebraic method and putting it into a sliding window filter might get the same estimates as what you get?
No, but the problem with the algebraic methods is when the translation is small.
Okay, this one aside. Okay,
yeah.
This one is more a problem of what the method provides you.
Okay.
But for the over.
Yeah. So when the method does not fail, I haven't done it actually. But one of the works is also then to do a comparison. So using like a filter you said, and then what we obtain, and actually do a comparison between the outputs what we obtain from both these measures. So this is one work what we have not done, and this is one of the works which we want to do actually. But the main motivation of not doing this work was that since you don't have, you're not able to obtain any algebraic solution for the degenerate case. So at that point, the algebraic method fails. So even if you apply a filter, it's not going to work because you don't have a solution. So.
But, okay. I don't know if the biggest effort is really here because when you're stabilized, somehow you're using your motion to. You don't need a precise estimation at this time. Okay. It depends on the application.
Yeah.
Okay. Just thinking around. Okay. That's all for me. Thank you. So, Vincent.
Thank you very much for inviting me, and congratulations for your manuscript, which was very clear, and for the presentation, which was enthusiastic and clear and provided some more information. I agree with Julien about the fact that this application should be very interesting also at the end of the manuscript, but not everything is included. I also have a remark about the bias of the gyro, as you pointed out just a few minutes ago. You say that you measure them at steady state, but in fact they can double after 5 to 10 minutes. So
this is one of the issues where we had to do a calibration of the GROs after especially with the peaks of IMU.
Yes.
There were many instances where after 3 months or something like that, but we had to do a recalibration of the GROs again.
Yes, but even after 10 minutes, because you have a drift with the temperature, which is very, very, very big.
Yeah.
And for marine application, well, finally, you never do a flip and then come back, so the mean of the gyros needs to be 0 all the time, except if you do turn all right in the same direction. So something I do, which is very simple and can maybe help you to estimate the bias, is just you do the mean along, let's say, 10 minutes, and this is the bias. For marine robots, it works very, very nice. So it's maybe a simple way to improve this. Could you please go to the slide number 20, please? And 20, because yes, I'm too far to read what is the unit of the.
It's 1 hour.
This is the depth.
Yeah, it's 1 over d actually.
1 over d.
1 over the depth.
Over the depth. Okay. So, and
around 1 meter more or less. So performing the experiment around at this level where I'm moving the camera.
Yeah. And so this is the good opportunity to talk about what Julien said also when suggesting to incorporate a depth sensor in your algorithm. Maybe this specific place where the robot is not moving could benefit from this, because if you don't have an aggressive trajectory, you cannot measure the depth. Okay. I have also question about the update rate. So you said it's 30 FPS.
About? Camera frequency, yeah, around here between 20 to 30 hertz, or sometimes we have a camera as well which runs around 50 hertz actually.
And with that, so like on embedded application, this is important because it changes a lot the dimensions of the computation system. Yeah. So did you study a little bit if there would be an interest in terms of accuracy of your system to increase or decrease FPS?
So yeah, so especially for aerial drones actually. So if we are running at, let's say, 50 FPS, then it would help definitely because we are getting images at a faster rate as well. So in order to perform the computation as well, it would help.
And I could ask the same question for the image resolution.
No, that's
so
a big difference.
What is the trade-off between decreasing the resolution and then increasing the FPS? And then wouldn't it? Oh, sorry. No, I can ask the second part of the question.
So for us, we can work with VGA images as well. So performing homography estimation with VGA images is not a problem for us. So we would rather have a low resolution and a higher FPS rather than having a very high resolution and low FPS.
So the best is the low resolution and then higher FPS. Yeah. And also when you are trying to land, this is probably the phase where you need the highest FPS. Yeah. But this is also the phase where you are closer from the floor. Yeah. So you don't need a high resolution because the details can be seen very well. So did you try, or do you think that in the future you can adapt the FPS or the resolution depending on
that is one of the pyramidal things which we spoke about as well actually. So as you can take different reference pictures and you have a different resolution of the reference image. So this is one of the things where.
And this you can estimate it just by.
So the homography, I mean, it works up to. Since we have tried it up to 30 centimeters from the target as well. So it's like you're almost at this level, and you're still able to obtain the homography. So the 4 points which you saw on the drone on the target. When the drone was landing, so we were able to obtain the 4 corner points even when we were at this depth actually, around 30 centimeters. And even we have tried, it was in our interest as well to see until what depth we are able to still, where the homography still works actually. So even with these vehicles, we have gone up to nearly 30 centimeters and it works well.
Do you see a metrics in the image processing that you could use to define the optimal resolution to optimize the FPS? I mean, the level of detail that would say that you are close enough to decrease the resolution. I don't know if I'm clear.
Okay, so as you go closer?
Yes, something like an automatic metrics helping you to decide when you can decrease the resolution without decreasing the performance.
Let me just quickly have a minute to think. I think yes. But let me think what we do right now is we go close. We can. So actually taking into account the distance to the target and even the number of features basically what we have, using those 2 quantities, we can actually change the resolution of the image close to the scene. So this is something which.
And You mentioned that the DVL does not work very well when you are close to the seabed. This is perfectly true. But when you are far away from the seabed, let's say 2 meters, then I think the optical will be. So there's a
trade-off between, because at 2 meters actually you may not be able to see, let's say, the images as well. So in such situations, a DVL would be better in order to have the measurements. But some of the applications we work on is more related to, let's say, station keeping, where we are in close interaction with the environment as well.
Exactly, it clearly depends on the application. Because if you are far from the structure and if you push the water along the structure or along the seabed, then you cannot see anything anymore.
Depends on the turbidity as well. So in such situation, I mean,
your method should be, and I mean, you told it, at lunch it's robust toward turbidity, but when you come and push the sediment with the thruster, then only the DVL will work. So, but for application of monitoring far away from the seabed, for photogrammetry, for instance, I think your system is perfect. So once again, congratulations, and also congratulations for the industrial transfer, which shows that your work is working very well. Thank you.
So before letting your supervisor say the final words, I have also a couple of questions. I'm sorry when you are tired, but so the first question is about the convergence domain of the Kato observer. So it's based on first order estimation. So have you tried to analyze this domain, or maybe in the simulation to try to big perturbation to see how far it can go?
frankly speaking, I haven't done this analysis actually.
So this is